Hello again, this is Tim Undorf with Midwest Laboratories. This will be part 2 of our how to interpret soil test results. In the first video we looked at some of the basic properties of soils that you can see in a soil test. We looked at cation exchange capacity, we looked at organic matter, and we looked at soil pH as well as the buffer index used for making liming recommendations. So from there we're going to move on to the actual nutrient analysis, and a lot of people like to jump forward to phosphorus and potassium and sulfur and zinc and what they're going to look at spending fertilizer dollars on. We wanted to set that stage earlier on just looking at the soil itself, that cation exchange capacity, looking again at nutrient and water holding capacity, workability, soil texture, organic matter and its ability to supply nutrients, and then the soil pH, that chemical balance in the soil that may keep nutrients available or make them less available. So we wanted to start there, but now let's move on to phosphorus, potassium, the other cations, and we'll look at the base saturations in this video as well. So we're going to start with phosphorus. If you look at a Midwest Laboratories soil test, you'll see 3 different phosphorus tests right off the bat. We've got the P1 Bray or weak Bray, we've got the P2 or strong Bray, and then we've got the Olsen bicarbonate P test. And we see that Olsen test is not run on the majority of soil samples, at least in this report. It's just run on one of them. And why that is we only run the Olsen in high pH soils where we think that the soil's pH might actually be interfering with that P1 Bray analysis. So we'll start with the P1 and P2, and then we'll talk about the Olsen and walk through it on this higher pH soil. Well, let's just start with the P1 Bray. At the laboratory, we use the P1 Bray test for the majority of our phosphorus recommendations. We also run a P2 Bray, which is basically an extract solution with about 4 times the acidity of the P1 Bray solution. And what we expect in that P2 is a number that's about double the P1 Bray. So back to the P1 Bray, we like to see our soil samples running for most crops around a 20 to 30 part per million. 20 part per million is about the lowest we like to see. Somewhere around 20 to 25 is probably a pretty good range to be in. 25 to 30 is a really strong, high fertility soil. So if we're below 20, we're going to be making a recommendation for phosphorus. It generally is going to try to build to around that 20 part per million and then maybe replace some crop removal on top of that. If we're above 20, then we're probably just going to try to keep it in that range by replacing crop removal. If we get much beyond 20, say into that 30 plus range, then we'll start making recommendations that are just a portion of crop removal and let the crop go ahead and mine the soil test levels down. So with those numbers in mind, we can kind of look through these samples here. And of course, as we talked earlier in the previous video, these samples are across a few different states, Iowa, Nebraska, and South Dakota. But as we look at each sample individually, we can see an 18 part per million here on this first sample. So there we'd probably be making a recommendation to try to build it a little bit, but we're not too far off of that 20 part per million. It would kind of be the lower edge of where we'd want to be. And again, at the laboratory, when we're making recommendations, we're going to adjust them based off the yield goal that the producer gives us. So if you're shooting for very high yield corn or soybeans, let's say that might be a 250 bushel corn crop or an 80 bushel soybean crop or a 100 bushel wheat crop, we might push those numbers up a little bit higher. And for lower yielding environments, say 150 bushel corn or 40 bushel beans or maybe a 60 bushel wheat crop, we might shoot for numbers a little bit lower than we might target for those higher yields. But again, like I said earlier, with an 18 part per million P1 Bray, we're probably going to want to build that a little bit and also replace crop removal for whatever crop that we're putting in there. At a 10 part per million, we're also going to be looking to build and replace crop removal. We get to 21 part per million, probably also looking for a slight build, again, depending on what our yield goals are, but certainly we'd want to replace crop removal and wouldn't want that number to go down from that. And then we get to a little different story here as we looked at this central Iowa sample at 99 part per million on the P1 Bray. That's really telling me that we've got plenty of phosphorus, and there probably wouldn't be much reason to add additional phosphorus there. You know, if you're using a starter fertilizer, I certainly wouldn't hesitate to continue to put a starter down, but that's about all that I'd want to put down in an environment like that with plenty of phosphorus. When we see numbers that high, sometimes we kind of question maybe why the number would be that high. When you've got numbers, phosphorus numbers at near 100 part per million, generally that's going to indicate maybe some manures have been applied in the past. And in this case, I would say that that's probably the issue. Now, we don't see the potassium number being all that high, and a lot of times with manure, it's going to affect phosphorus, potassium, and oftentimes zinc as well. As I look at phosphorus, certainly that would indicate maybe some high fertility that might come from repeated manure applications. The potassium really doesn't make me think that, that manure is necessarily the issue. But then I go look down at the zinc on this sample, and this is the fourth sample down with the 99 part per million P1, the 129 part per million P2. We go to the zinc and we're at 11.6 part per million, which is very high. Those numbers combined would make me think that this is probably a field that's received quite a bit of manure in the past. So recommendations in the future would probably be very little application, and let's try to mine those numbers back down to lower numbers anyway. We get to this fifth sample down that came from eastern Nebraska. See 61 part per million on the phosphorus P1, 117 on the P2. Also high on potassium at 435 and nearly 4 part per million on zinc. Could be manure in this case. Could also just be some high fertility fertilizer applications from the grower. So the grower probably pushing fertility a little more than normal to get to a 61 part per million, or it could have been manure. Move a little further down and we see these 9 part per millions here in northeast Nebraska. Now in this first sample here from northeast Nebraska at 9 part per million, we've got an 18 part per million P2 bray. I said earlier we like to see that ratio between the P1 and P2 about a 1 to 2, and that's what we see here. I look over here and I see that this is that very light CEC soil, so probably quite a bit of sand in it. See fairly high potassium numbers for that soil really, but at a 9 part per million P1 and an 18 part per million P2, it's telling me there's not a lot of reserve fertility behind that P1. And with this being a lighter soil, I'd certainly want to get on top of making fertilizer application on that soil. This next one down, the western Nebraska soil, we've got a P1 of 9, but a P2 of 130. Like I told you earlier, we'd like to see that P1 to P2 ratio at about 1 to 2. If it's higher than 1 to 2, so like it's 1 to 4, 1 to 5, 1 to, in this case, over 10, it tells me there's a lot of fertility behind that P1 bray that's not being shown in the P1 bray. Again, this soil was our high pH soil, so when I've got a soil with a pH as high as an 8.3, it makes me wonder if maybe the soil's pH isn't neutralizing this acid extract solution that we use for the P1 bray. I mentioned that the P2 bray is about 4 times acidic as the P1, so obviously it's not having so much of a problem finding phosphorus, but it looks like maybe the basic or causticness of the soil itself might have neutralized that P1 bray extract solution in this case, especially when we see the P2 at 130. So in this case, with that high pH soil, we went ahead and ran the Olsen bicarbonate test, and that Olsen showed us that there was quite a bit of fertility there that wasn't being shown in the P1 bray, and we come up with an Olsen value of 23, which is quite high. So when we talk about phosphorus test results and the numbers we're looking for, I kind of gave you a number of around 20 to 30 is a pretty good range that we'd like to be in with that P1 bray. When we're talking about the Olsen, it's a little bit lower scale. So a lot of times with the Olsen test, we'd want to be somewhere in that 15 to 20 range instead of the 20 to 30 that we'd like to see in the P1 bray. So even though the Olsen is at a 23, which seems like it's kind of a medium level, actually because the Olsen scale is a little lower, the 23 is actually quite high. So with an Olsen test running at 23, that's probably going to call for at most crop removal, and probably a little bit less than crop removal is the recommendation that we'd make. The scale for Olson, again, runs a little bit lower than what it does for the P1 Bray, and I would consider that 25 to be pretty high, and that's what we show here. When I look at that P2 number, so a lot of people will question why the laboratory runs both the P1 Bray and the P2 Bray. For us, it's an internal quality control. We're looking to basically double check that phosphorus number and make sure that it's accurate. And when we see numbers that are a lot different than that 1:2 ratio, we might go ahead and run a sample again, unless there's something like the soil pH or an Olson number that would make us confident in that initial result. So this is a quality control for us. Some things like the P1 Bray would always have to be lower than the P2, given that the P2 is much more acidic than the P1 and should always show higher phosphorus. We'd know that maybe we'd gotten something out of order if the P1 Bray would ever show a number higher than the P2, so that would cause us to go back and run samples, rerun these samples and possibly samples around that, again as a quality control to make sure we've got everything in the right order and to make sure that our phosphorus tests are coming back accurately. So the P2 basically just gives us a second look at our phosphorus and also gives us some additional information about the reserve fertility that's behind that P1 Bray number. So some laboratories, especially in other countries, will run a test that's called the phosphorus buffering test. And for us, this P2 test is a little bit like that. It shows us some of that reserve fertility that's behind the P1 Bray results. Again, when we run the Olson, then what we're looking at a lot of times is we're questioning if a basic soil may have neutralized the extract solution for the P1 Bray. And when we think that might be the case, we will run this Olson bicarb test. And in this sample for western Nebraska, that was true, that the P1 Bray had been neutralized by the basicness of the soil, so we ran the Olson and found out that there's quite a bit of fertility that was not being shown by the P1 Bray, although the P2 Bray also gave us a clue that that's what was going on. As we move on to those South Dakota soils, we've got a couple that are at kind of normal to slightly acidic pHs, a 6.2 and a 5.9, so really no reason to run the Olson. The P1 Bray, we find a 16 here with a 32 on the P2 behind it. Again, we're going to want to build that so we're up into the 20 part per million range and replace crop removal. And then this last sample, the eastern South Dakota sample number 2, comes with really good fertility, a 31 on the P1 Bray, a 56 behind it, which is showing about that 1:2 ratio we were talking about earlier. So in this sample, we're probably just going to replace a portion of crop removal or maybe even make no recommendation, again, depending on what that grower's yield goals are. If he's got more aggressive yield goals, pushing for higher yield, we'll go ahead and keep making some recommendations into these low 30 numbers. If he has lower yield goals, we'll probably cut those recommendations back to very small recs. And that pretty well covers phosphorus. So again, in review, the P1 Bray, we're looking for a number around 20 to 30 part per million. So for the P2 Bray, since we'd like to see that ratio at about 1:2, then the P2 we'd like to see a number somewhere between 40 and 60 part per million. If we're lower than that 1:2 ratio, it really gives us an indication that maybe there's been some mining in the past and the reserve fertility that's behind that P1 number really isn't that good. And we probably should be pushing to go ahead and get those fertilizer recommendations made and applications made because fertility is definitely an issue, or phosphorus fertility is definitely an issue in that field. When we see numbers that are higher than the 1:2, so we've got a 1 to maybe 4 or 1 to 6. In the case of this sample from western Nebraska, that ratio was actually greater than 1 to 10. It tells us there's a lot of fertility that's not being shown in the P1 Bray. And in this case, we went ahead and ran the Olson and found that that P1 Bray had been neutralized by the basic soil, and the Olson was a more appropriate number to use to make fertilizer recommendations. When you go to compare the Olson to the P1 Bray, because again there's a difference in scale, in a P1 Bray, a medium soil might be considered, somewhere between 18 and 27 part per million, whereas in a Olson, a medium might be somewhere more like a 8 to 17 part per million. We run a multiplier of about 1.4. So if you take the Olson times 1.4, that would be a number that you could compare to a P1 Bray result. So this 23 times 1.4 is going to give me a P1 Bray equivalent of about 32. So again, it probably not a lot of need for additional fertilizer applied on that soil unless the grower is going after some very high yields. So from phosphorus, we'll normally move into potassium. And in the case of potassium, the number we really would like to see at the laboratory is probably around 200 part per million, but that's going to vary a little bit with how heavy that soil is. We talked about cation exchange capacity and the ability of soils to hold additional nutrients. So in a lighter soil, we might shoot for a little bit lower target in the potassium level, and for a heavier soil, we might shoot for a little higher target. So if on a normal soil of, say, 15 to 20, 22 CEC, we're probably shooting for about 200 part per million. As we move into soil that's a little heavier, has more clay in it, more in that 25 to 30 CEC range, we might shoot for a little higher target, more like a 220 to 250 part per million potassium. And in a lighter soil, let's say under 10 CEC, we might shoot for a target more like around 170 to 180 part per million on those potassium numbers. So as we look through these samples here, the first couple here in western Iowa are both below that target that we're shooting for of about 200 part per million. This 139 part per million, we'd want to build that some in addition to replacing crop removal. The 188 is not too bad. Probably would want to at least make sure we replace crop removal in that soil. And again, these CECs and these two are both right around 20 CEC. We've got a third soil here that's a little heavier. That was our one that was around a 25 CEC. So this 250 part per million is probably a number that's about right. We might make a slight recommendation in that soil, but it wouldn't be a very large recommendation, probably just a % of crop removal. So we move along through here, continuing with those potassium numbers. This central Iowa soil with the 288 part per million, a CEC of 18. It's probably a pretty good number. We probably wouldn't have much of a recommendation on that one at all. Again, it's going to depend a little bit on that grower's yield goals. If he's shooting for 300 bushel corn, we might continue to make a bit of a potassium recommendation, but if he's only shooting for, say, 180 or 200 bushel corn, we'd probably have very little rec. Eastern Nebraska soil here, we've got some very high fertility, 435 part per million. So a lot of potassium in that soil, probably wouldn't have much of a recommendation there at all. And then this northeast Nebraska soil that was the very light soil with a very low CEC, this 210 part per million, which you might consider kind of average for a more medium texture soil, is actually quite high for as light as this soil is. So we'd probably have very little recommendation in that soil. Probably a portion of crop removal, but probably wouldn't level at all. In this western Nebraska soil, fairly high potassium numbers as well at 434 part per million. Probably not much reason to build that soil at all. If we were to make any recommendation at all, it would just be a small portion of crop removal. And actually our recommendation from the lab would probably be no application. The first South Dakota soil here, we've got 160 part per million. Soil's kind of medium textured here, looking at this 18 CEC. So we'd like it to be a little higher than that on the potassium results. So we'd be shooting for a recommendation to both build soil test levels a little bit and also replace crop removal. And then the last sample here at 245 part per million. Again, fairly medium textured soil. We're probably not going to try to build the potassium results much beyond this, but we would want to kind of keep them in this range, so we might do a recommendation that was a portion of crop removal, but not much beyond that. And again, it's going to depend a little bit on what that grower's yield goals are. If he's trying to push very high yield goals, say 280 to 300 bushel corn, we might go ahead and make a full crop removal recommendation. But if he's below that much, we're going to do just a part of crop removal. And if his yield goals are more like around 180, we probably wouldn't make much recommendation at all. So that's kind of the mindset, again, in our recommendations. We're shooting for around 200 part per million. We might vary that a little bit based off how heavy the soil is, and certainly we're going to vary that some based off the yield goals that the grower's pushing for. And that's going to be the case for potassium. For phosphorus, we're certainly going to look at trying to get ourselves into that 20 to 30 part per million range. Once we're there, we're going to want to replace crop removal. It's going to base that a little bit on what the grower's yield goals are again. In the case of phosphorus, we don't look as hard at CEC. So that covers the recommendations and kind of the analysis we're looking at for phosphorus and potassium. Let's look at magnesium and calcium a little bit. On the magnesium side, most of the soils we run into have plenty of magnesium in them, so we don't make magnesium recommendations very often. But in this case, we do have one soil here that is actually a little lower in magnesium, this 127 part per million on this very light soil with the 5.8 CEC. Even though we show this is very high because it's got quite a bit of magnesium for as light as that soil is, still might limit yield possibly. Again, depending on what that grower's yield goals are. If he's pushing for high yield corn, say 250 to 300 bushel, or high yield soybeans in that 80 to 100 bushel range, we might go ahead and push back for a little bit of a magnesium recommendation here, just because he has such low levels, which are mainly due to how light that soil is, its inability to hold nutrients, especially the cations, potassium, magnesium, calcium. So I might look to make a little bit of a mag rec on this soil at 127 part per million. Everything else on this report with these 300 to a high of 700 part per million, there'd be no reason to add additional magnesium that I could see. We might actually have some concerns here with these 600 and 700 part per million magnesium levels, that there's too much magnesium in that soil. That could be interfering with uptake of other cations, or maybe just creating some issues for difficulty for water infiltration. So we might actually look to see if we could reduce those magnesium levels a little bit. And we'll talk about that as we move on to base saturations. But before we get there, let's look at calcium. Our calcium numbers, as we look across these soils, somewhere in that 2,000 part per million range. Again, it depends a lot on how heavy the soil is or how much clay is in that soil, on what numbers we're looking for in calcium. I frankly spend more time looking at my base saturations on magnesium and calcium than what I do on my part per millions, with the exception of those really light soils like what we have here with this CEC of a 5.8. Like we said earlier, you might want some additional magnesium, especially if you're pushing for very high yield with only 127 part per million here. On the calcium side, generally I let liming take care of calcium needs, and here we do have a fairly low pH at this 6.0, especially for as light as this soil is. Probably the right thing to do here to bring those calcium levels up a little bit would be to lime this soil with either ag lime or Pell lime. It's not going to be a very large recommendation because your buffer index number here is fairly small, but say 700 pounds of Pell lime, or maybe 1,500 to 2,000 pounds of ag lime might be a good way to go ahead and bring this calcium number up, and also bring the pH up as well, and counter some of the additional acidity that I assume we'll be adding as we add nitrogen fertilizer in the future. So there's our walk through the cations, potassium, magnesium, and calcium. One thing I didn't mention here is sodium. We do have the one sample here, the sample from western Nebraska with the 8.3 pH. It also has quite a bit of sodium in it. We see the eastern Nebraska soil, since we ran a complete analysis on it, it did give us a sodium number. 12 part per million is pretty much negligible, and I would say some of these other samples might have had equal or higher amounts of sodium. We just didn't run that analysis on those. Some of these we took from more of a grid sample basis. But in the case of this eastern Nebraska soil, it was from a composite where we looked at kind of the complete analysis of that soil. 12 part per million is not a number I'd be concerned about. But 160 part per million, that could be a bit of an issue. This is a little heavier soil, so it's got some buffering capacity. But when you get to numbers at 160 part per million sodium, you might be worried about some effect from that sodium, especially on the ability of plants in that field to take up water. A lot of times sodium will work against the plant in an osmotic pressure, which basically is saying that the soil is holding water, or the salts in the soil are holding water away from the plants. I like to combine that look at sodium with the soluble salt number, or what we call the electrical conductivity number. As we look at this sample for EC, we've got 161 part per million sodium. The EC is a 0.5, which really isn't too bad, so it doesn't look like the sodium is overwhelming the soil as far as a soluble salt number. Again, that part of that has to do with the fact it's a heavier soil with quite a low clay in it, with basically a CEC of 21. But I would have some concerns here. It might make some sense to add some gypsum to this soil to try to wash the sodium out of the profile a little bit, so that especially the soluble salt number wouldn't get worse in the future. You might check why you have higher sodium. Some soils just have natural levels of sodium that are a little higher. Sometimes sodium levels will build up because of drainage issues with a soil. So if you might have drainage problems, that sodium could collect there. Or if this is under irrigation, you might want to check your irrigation water and see if it has very high sodium levels in it as well. Now, this ratio between sodium, calcium, and magnesium in the soil also makes a difference. So again, it goes kind of back to that buffering capacity. If you have fairly high calcium and magnesium levels, the sodium, a higher sodium level isn't as much of a concern, but can be a problem if it continues to build. So that'd be something I want to keep an eye on in my future sampling. I wouldn't necessarily jump at making drastic changes, but might consider a gypsum application to try to bring this down. Again, you've got to look at how your crops have done in the past. Are you having issues with wilting or with the ability of the crops to bring up water? And if you are, then maybe you should get on top of it. All right, so that covers our cations. Let's move on to our base saturations. When it comes to base saturations, we've kind of got a range that we're looking for in most of our soils. We'd like to see that potassium base saturation be somewhere in that 3 to 6% range is where I like to see it. On the magnesiums, I like to see those somewhere in that 12 to 15%. On the calciums, I'd like those to be at least 65%, somewhere in that 65 to 75% range is where I'd like those base saturations to be. And then we've got a hydrogen base saturation here. I'd like that hydrogen base saturation to be under 10%. And that usually is going to correspond with a pH somewhere around 6.5 or above. So those are the ranges I'm looking for. Again, potassium somewhere between 3 to 6%, magnesium somewhere between 12 and 15%, calcium between 65 and 75%, and hydrogen somewhere under 10%. So as we look at those base saturations, we want to ask ourselves, why is that number lower than that range we'd like to be at, and what should we do about it? And that's always a tough question. So from a laboratory perspective, there's some people that make their recommendations based mainly off of base saturations. There's other people that make their recommendations based mainly off part per million. At Midwest Laboratories, we make our recommendations mainly based off of part per million, and as a consultant, I do the same thing. But I do look at my base saturations to try to get myself in that range that I'd want to be at. So as we look through these samples, from a potassium perspective, sample number 1 here is well below that 3% range, so are samples number 2. Sample number 3 is a little closer to that 3% range. So over here on the part per million side, we were going to be making recommendations to build these soil test levels because we're well under the 200 part per million with the second sample. So in both those cases, we're going to be making recommendations, and as we raise the part per million in the soil, we'll raise the base saturation. So both my base saturation of potassium and my part per million of potassium are calling for additional potassium to be applied to this soil. So really not much disagreement there. On the third sample, the part per million is showing quite a bit of potassium there and probably wouldn't call for additional potassium to be applied. And the percent K is showing us that maybe we are a little under that percent base saturation that we'd like to be at. And the main reason for that is this is a heavier soil with nearly a 25 CEC. So because of the additional clays here, there's more potassium and cations in general tied up. You might make a recommendation for potassium based off of this base saturation. That's really between you and your agronomist on whether they like to build their recommendations based off of part per million or off base saturation. So I'll just leave that up in the air, but I personally would probably not make much of a recommendation on that soil. So soil number 4 here, we've got plenty of potassium in the part per millions over here. We look at the base saturation, we're well within that range that we want to be in. Again, that 3 to 6 part per million, or 3 to 6% base saturation. So as we look at this lighter CEC sample here, with a 5.8 CEC, its base saturation is quite high at 9%. Its part per million is high, and it's higher than that 200 part per million that we said we were kind of shooting for in the average soil. And again, because this soil's lighter, we might want to shoot for a little bit lower part per million, maybe more that 160 to 170, but again, depending on that grower's yield goals. But this higher number gives me plenty of potassium from a base saturation standpoint. The sample here from western Nebraska, again, a pretty good amount of potassium as far as base saturation is concerned at 5.4%. And when we get into these two South Dakota soils, again, I said I want to be between 3 and 6% base saturation for potassium. The first one here, I'm only at 2%. And I also on the part per million and down to just 160 part per million potassium. So, both from a base saturation standpoint and from a part per million standpoint, we're going to be making a potassium recommendation. The other South Dakota soil here with a 3.2% base saturation, it's within that range I want to be at, and from a part per million standpoint at 245s, in a pretty good place there as well. So that's kind of how I tie the percent base saturation for potassium to the potassium part per million, and then kind of use the percent base saturation to confirm or maybe adjust my recommendation slightly based off part per million. But again, it depends a lot on the individual grower or the agronomist on whether they are more of a believer in the part per million or the percent Ks. So at the laboratory, we try to stay kind of neutral on that and let the end user decide how to use the data. I'm just trying to present both sides to you here in this video. So let's move on to percent magnesium base saturation. Like I said earlier, I want to be somewhere in that 12 to 15% range. This 14.7%, kind of right in there. Maybe it's just a little bit high, but again, I need to bring my potassium levels up through application, and I also need to bring my calcium levels up through lime application. Those two things will probably bring these numbers up and maybe make the percent mag a little lower as the whole. Sample number 2, fairly high magnesium. Sample number 3, also fairly high magnesium at 19% of base saturation. Might have a little concern there. You can use gypsum to try to bring down magnesium base saturations and bring up the calcium base saturations. In the case of sample number 2 with a pH of 5.6, before I did that, I would probably go ahead and get the liming done to bring this pH up, and that'd be the case of both samples 1 and sample 2, and those are going to bring these calcium base saturations up and may change the magnesium base saturation slightly and move those down a little bit. So first I'd take care of that liming issue before I tried to jump on the gypsum application to bring down the mag percent. Sample 3 here, from a pH standpoint, it's very good, but we do have high mag, so I might consider some gypsum to try to adjust that mag percentage down a little bit. Samples 4 and 5, so here we're on that central Iowa sample, and then the eastern Nebraska sample. I said I wanted to be between 12 and 15%. These are right in that range. They're just slightly high. I wouldn't worry about them too much. This northeast Nebraska sample, I said I actually needed some magnesium on a part per million standpoint, just for the crop having enough magnesium. From a base saturation or exchange site saturation standpoint, it looks like there's plenty of magnesium here, but really, even though the balance is fine, I'd be a little bit worried about just not having enough magnesium in that overall amount that the crop needs, just because of how low those numbers are. So, those base saturations, you also need to look at your part per millions as well, because it may change your mind on what you do. All right, on this sample from western Nebraska, I'm kind of just a little on the high end of that range that I wanted to be at. I said 12 to 15 was a good range I'd like to be at. It's a little high at 17. I don't think I'd be too concerned about that. And then these last two, they are quite high. So again, I said 12 to 15 is kind of where I want to be at. Here I've got a 27 and nearly a 31. In the later samples case, it certainly does need some lime to bring up the soil pH and reduce that acidity, so I definitely need to make that amendment, and that might help balance this out a little bit and bring up this calcium percentage. but I'd still probably look at maybe some gypsum to try to break loose a little bit of that magnesium and try to replace some of that with calcium on the exchange sites. So might do the liming first and see what change that made, but I would suspect I may end up coming back with some gypsum to try to lower those mag percentages a little bit. So again, looking at those mag percentages, most of them look pretty good with the exception of those last two samples. Those are quite high, and those would be something I might want to go after. So let's move on to the calcium base saturations. I said I want to be between 65 and 75% on the base saturation. Samples 1 and 2, the obvious answer to that is let's lime it. Lime it to fix the pH issue, which is actually, I would say, higher on my priority list than base saturations, but I'm going to gain the benefit of a better balance of my base saturations by the calcium I'll gain from adding lime. Sample number 3, everything looks fine. Samples number 4 and 5, these are the central Iowa and the eastern Nebraska. Just by coincidence happen to have pretty much the same percent calcium on the base saturations. They look fine to me. I wouldn't have any concerns there. I'm right within that range I want to be at. This northeast Nebraska soil, again, this very light soil with an acidic pH, and we said it was probably a little low on calcium. Let's go ahead and knock out 2 birds with 1 stone there. Get that liming application made. We'll correct that acidity. We'll bring up the calcium part per million, and we'll also bring up the calcium base saturation percentage. So I'd say, again, a light lime application will probably take care of all of my woes there as far as both calcium from a part per million and a base saturation standpoint, and probably more importantly, that lower pH acidic soil. Western Nebraska, we know that soil had a higher pH. We see plenty of calcium in that soil from a part per million standpoint, and the base saturation is one of the highest ones, or actually the highest one on this report. In these last two here, we've got a little bit of an imbalance, I would say, between magnesium and calcium. I talked a little bit about gypsum to bring down that magnesium. The same gypsum, of course, is going to bring calcium into that soil and going to correct that base saturation calcium a little bit. And of course, this last sample, we've got some acidity there, so liming to correct that acidity and bring up that pH is also going to help me correct this base saturation imbalance and fairly low calcium number. The percent hydrogen on all of these samples, in every case that we've got a percent hydrogen that's above, say, 15%. In all of those cases, we need to add lime to correct the soil acidity, and adding that lime will break this hydrogen loose and correct the acidity. A lot of this hydrogen will end up being converted to water through the reaction of lime and that free hydrogen. And then that's going to bring down these hydrogen percentages, and a lot of that will move right into these calcium percentages with the calcium from the calcium carbonate of the lime will come on here on these exchange sites and replace the hydrogen and correct that reserve acidity, and that's what's going to bring up these base saturations of calcium as well. So the liming to correct the acid soil is going to correct a lot of these imbalances we see between hydrogen and calcium on the base saturations. And then on the sodium side, we've only got 2 soils where we've looked at sodium. This 12 part per million and 0.3 base saturation is pretty much something that's not an issue. This 3.4% base saturation, for the most part, any sodium is not what we want to be seeing. So as we see percentages move above 1%, it's something we should at least be paying attention to. Fortunately, this is a slightly heavy soil with quite a bit of clay in it. That's going to help buffer some of the negative impact of that sodium, but I still would be thinking about maybe some gypsum to try to bring those sodium numbers down and make this go away. So that's going to end recording number 2. We'll have a part 3 where we look at nitrates, sulfur, zinc, and the other micronutrients. But this is going to end our presentation on phosphorus, potassium, the other cations, and the percent base saturation. So thank you, and please come back for recording number 3.